Okay, so we're going to talk about rotating a vector in some degrees. You can see here theta. Theta defines the degrees. So you can see how the degrees change as the vector is rotated. And we are going to talk about rotating a vector 90 degrees in the counterclockwise direction, but the same thing. So we are going to talk about the rotation matrix and how it can rotate a vector. This case is in 2 dimensions, but we are also going to talk about rotating a vector in the 3D dimensions. Okay, so let's start doing it. So we're starting by showing you the rotation matrix itself. You can see here that this matrix, this is the rotation matrix. This is in the 2-dimensional space. This is an orthogonal matrix, namely its transpose equals its inverse. And as an orthogonal matrix, it preserves the norms of the vector, so it won't change the size of the vector, but it will change the direction of the vector as orthogonal matrices do. So this is the rotation matrix in the counterclockwise direction in the 2-dimensional space. You can see here the cosinus and the sinus and the minus sinus right over here, and the theta, which defines the degree by which we change the direction of the vector. So, for example, if we have a vector x and y, we are going to multiply, in order to rotate the vector, we're going to multiply the matrix with the theta we want by the vector and getting a new vector with the new coordinates rotated as we want theta degrees. And then we said in this case we're going to go counterclockwise and not clockwise. So let's see an example. So here is the rotation matrix, the counterclockwise rotation matrix with 90 degrees, and we're going to rotate a vector of 1, comma 0. So you can see it right over here. When we multiply from the left this vector, we are getting, as you expect, instead of the vector going in the x direction, it will now go in the y direction, for example. Okay, so this is exactly 90 degrees counterclockwise of this vector. So this is how the 2-dimensional rotation matrix works in rotating a matrix counterclockwise. Let's just look on the 3D rotation matrix, 3 dimensions. So we have 3 rotations for each axis. For the x-axis is this one, quite similar to the 2 dimensions, but we have another row and column. The y rotation, again, quite similar, but we have another row and column, and the z rotation matrix. Now we're going to take a vector and rotate it. So let's see how it works. We are taking the rotation matrix and we take the vector 0, 1, 0 and rotate this in the x direction. This will give me the z direction. Okay, so instead of y axis, now it points along the z axis according to the right hand rule that predicts it, right? Okay, anyway, this is how the rotation matrix on 90 degrees looks in the 3 dimensions. I just plug in the 90 degrees, plug it in on this case. Now there is one here, but I plug in 90 degrees right over here, and we got this matrix. Okay, so this is the 3-dimensional rotation matrix for a vector, and generally those are the rotation matrix in the 2-dimension and 3-dimension. Again, remember that those are orthogonal matrix. So again, all the properties of orthogonal matrix apply here. They retain the norm of the vector. As you saw, we have the norm doesn't change, and you can know that the transpose equals inverse. We didn't use it right over here, but remember that those rotation matrices are orthogonal matrices with all the properties of orthogonal matrices. Okay, so you can see, for example, all the columns of the rotation matrix are orthogonal to one another, right? So you can see that it will show you how it is. This is the property for orthogonality, and you can see that if we take the dot product of the 2 columns, we are getting 0 by definition. because this is an orthogonal uh, matrix. So the columns are orthogonal to each other. And this is the property of orthogonality. Okay, thank you very much. This was about the rotation matrices. If you have anything to say, please leave a comment below. And that's it for now. This was about the rotation matrices. I think this is enough. And we all started from this one. But again, we are not going the clockwise direction, we're going the counterclockwise direction. So remember that this is just to the other direction. Yeah? Great.